let f be a function defined above, for what value, if any, is f continuous. So whenever we have a piecewise function, we're jumping between different functions, we need to make sure we don't have a jump in our problem like that. We need to make sure that these two pieces line up. All right, another way of saying that is when we make the jump, we need to make sure these two things are equal. And at first this looks pretty difficult to solve, but we know this is happening at 3 is where we make that jump. So now I can change this to like that. Because we know it's at 3 is when x is going to be. And now we need to figure out the k value that solves this. So I'm going to do it in my calculator. So I'm going to graph. Instead of k, I have to take x. So it's going to be a little confusing because we already had an x, but I'm taking x cubed plus 3 is one graph. And another graph is 16 divided by x squared minus 3. And you may have to adjust your viewing a little bit, but you can see they cross each other at some point. And if you figure out where those two functions cross, the value where they cross is at 2.081. All right, so just using this idea of continuity means these two pieces have to be equal, and they have to be equal specifically when x equals 3. All right, the table above gives the values of a continuous function f, all right, at certain values. All right, which of the following statements must be true? All right, f has at most 1, 0, so this might seem true because if you have your points, if we think about our points, we have -5, -9, which would be down there, 0, 1, and 2, 5 would be up there. All right, so it seems like I might only have 1, 0 because I just kind of cross like that, but your function could cross a bunch of times like that. So this one's definitely out because it could cross much. All I have is these 3 dots. A lot of things could happen. All right, f has a relative maximum at x equals 2. All right, this is the biggest value we see, but it could keep going up after that, or it could turn down. It could be coming up and going down like that. So there's a lot of different things that could be happening too. All we know is exactly this one point. So that's not enough information to know it has to have a relative maximum. All right, there's a value of c between -5 and 2, such that f of c equals 4. So my output is 4. All right, well, if I start down here and I have to get up here, and it's a continuous function. So remember, continuous means you can't lift up your pencil. No matter what I do, at some point to get between there, I have to cross that line. So this one seems like it should be true. And that's actually the intermediate value theorem. And then D, there exists a value C such that the derivative is equal to 2. All right, this one's actually using the mean value theorem. And if you looked at the slope of the secant line, you would do -9 minus 5 over -5 minus 2. And you get 2. So the slope of the secant line here, sorry, I have so many colors going on, but that line that connects those 2 points, that has slope 2. So the mean value theorem says if there's a point where the derivative is equal to the slope of the secant line, so it seems like D should also be true. All right, but all we know about this function is continuous. We don't actually know that it has a derivative, so in order to talk about the mean value theorem, we have to know it has a derivative. And this one might not have a derivative because the graph might look like, instead of looking like this, it might look like this. And this has a bunch of places where it doesn't have a derivative because of all those cusps. All right, so we don't know this function is differentiable. So D actually can't work because we don't know that extra effect, which means C is the only option. All right, the function f is the antiderivative of the function g. All right, which of the following is the x-coordinate of the location of a local maximum of the graph of y? So they made it sound a little bit more complicated, but basically we have this function f. If f is the antiderivative of g, it also means g is the derivative of x. And if g is the derivative of x, when do we know f has a local maximum? Well, maximums look like that. And it's when my function goes from increasing to decreasing, which means my derivative goes from positive to negative. So anytime your derivative goes from positive to negative, your original function has a maximum. So what I'm going to do is just graph g, because g is the derivative, so 3 minus this square root. And we want to find when it goes from positive to negative. So there's a point on the left which is negative 3.961. That's when it's going from negative to positive. So that would be a minimum, because it would look like this. If the derivative goes from negative to positive, you get a minimum. But farther to the right, we have a place where it goes from positive to negative, just like we want, and that's at 3.14. Right, so right around pi, it seems like, you're going to get this local maximum for f, because its derivative, which is called g, goes from positive to negative. All right, this is a graph. What could be a graph of f prime? So remember that f prime, the derivative, is the slope of the tangent line. So if we think about all the slopes of this, it's going to be a constant slope because it's a line, and it has to be a positive value. So automatically I can cross out c, because c starts at a negative value. All right, and all the other ones start off with this positive value there. And then right away, it switches at this cusp and starts going down in the down direction. So right at 2, my graph is going from increasing to decreasing, which means my derivative has to jump from positive to negative. All right, so b is out, because right there, I still have a positive value, which would mean my function would be increasing, but it's not because it's decreasing right there. So I have to cross out b. All right, so now it's between a and d. All right, and at 3, our original function has a horizontal tangent line, so our derivative should be 0 at 3, which it's not in d, which leaves a as the only option. So just by process of elimination, knowing that increasing means your derivative has to be positive, decreasing means your derivative has to be negative, and minimums mean your derivative is 0. So putting all that together, a is the only option. Velocity of a particle is that. Let t equals b be the time at which the particle changes from direction from moving left to right. What is the total distance traveled by the particle during that time? So the first thing, if my particle is going from moving left to right, that means my velocity is going from negative to positive. Because negative means I'm going left, positive means I'm going right. So the first thing I'm going to do is graph this function. And I have to use x's instead of t's, but x sine of x cubed. And if you graph this on a big scale, it's crazy, but we only care about from 0 to 2. So 0 to 2. And the first time it goes from negative to positive is at 1.845. So that's the time when my velocity goes from negative to positive. So that's my b value. And now what is the total distance traveled by the particle? So if I want to know the displacement, I would just do this. So I'm going from 0 to time b of t sine of t cubed. So if I just care about displacement, this is what I would do. But total distance means I don't want anything to cancel out. So what I do to kind of fix that is I just put everything in absolute values. That makes it always positive. Nothing's going to cancel out. So now the last thing I do is just find this interval, 1.845. The absolute value, again, I have to use x's, x sine of x cubed. And that tells me it's 1.011, which is c. I have to forget the absolute values. Some things will cancel out and you'll get 0.212, which looks like A is the right answer, but things are canceling out and that doesn't give me the total distance. That's like if I go left and right, that cancels out versus the total distance. I want everything to be positive, so I use that absolute value. Let f be a function defined this way. For how many values on that interval is the instantaneous rate of change equal to the average rate of change? So the first thing, my instantaneous rate of change is the derivative. Average rate of change is the slope of the secant line. All right, so I want to know, when are these two things going to be equal? Well, the slope of the secant line is going to be when I plug in 1.565 and subtract when I plug in 0 over that. So just like a normal slope. All right, so I'm going to have to end up using a calculator for that. And the instantaneous rate of change is just f prime of x. So what I'm going to do is find the value of this and figure out when the derivative is equal to that value. All right, so the first thing, I'm going to type in my function. Then I want to do, when I plug in 565 minus when I plug in 0, all of that divided by 1.565. All right, so the slope of the secant line ends up being negative 0.392. And now I want to find when is my derivative equal to that. So the derivative of this I can find by hand. All right, f prime of x is going to be x cubed minus 2x squared plus x minus 1/2. All right, so that's my derivative function. So now I want to graph my derivative function. X cubed minus 2x squared plus x minus 1/2. I'm also going to graph the line y equals negative 0.392. I want to see how many times those hit each other. So that's one option. Another thing I could do is if I want to know when these two things are equal, all right, I could add this to the other side and figure out when that equals 0. And that might be a little bit easier to figure out what zeros are. So what I'm going to do is add 0.392. Right, how many zeros are there going to be? 1, 2, 3 zeros there, which means these functions hit each other 3 times, so C is the answer. All right, the scale on this one is really small, so it might be kind of hard to see, so that's why I think sometimes when you're trying to set things equal, if it's easy enough to just move this and figure out when it's equal to 0, rather than when these two separate things are equal, it might be easier to find on a calculator. All right, G is twice differentiable function such that its derivative and its second derivative are positive. We know G of 3 equals 12 and G of 5 equals 18. Which of these are possible values for G of 6? So we know we have 3, 4, 5, 6. Oops. At 3, we have 12. At 5, we have 18. And at 6, we have question mark. All right, so we know for this whole time, the derivative is always positive, so it's always going up, so we don't have to worry about this function kind of going down and back to 18. And we know the second derivative is also positive. So if something's positive and concave up, or sorry, increasing and concave up, increasing means like this. Oops, if I can actually draw correctly. Increasing means like this. Concave up means like that. And when you put them together, you get something that kind of looks like that. All right, so from 12 to 18, I'm going upward. That is a gap of 6. So we kind of break it up into 2 pieces. Those are gaps of 3. Which means this kind of curve up to 6, this gap here should be bigger than 3 because this is increasing more each step. It's getting steeper and steeper. So if this gap here averages a gap of 3, the gap here should average a gap more than 3. So from 18 to 6, we should be adding 3 or more. So if I add 18 plus 3, I get 21. So 20 is automatically out, which means C cannot be right. But we know it's strictly bigger, so if this gap is 3, this one has to be bigger than 3, so it should be bigger than 21, which means B is the only option, because it's increasing faster and faster each time. All right, the table above gives a function and its derivative. All right, G is the inverse. Find the equation of the tangent line at G at the point where x equals 2. All right, so we're going to find the equation line of G at x equals 2. All right, so here's what we have to remember. We have this inverse relationship happening with our original function, does x, y. Our inverse flips those. All right, so if we're trying to make this 2, that corresponds to the y value of my original function, which is that, which corresponds to 3. So if 3, 2 is on my original function, 2, 3 is on my inverse. So another way to say that, if I'm looking at point slope form, I know guaranteed that this function has y minus 3 equals m times x minus 2. And I can add 3 to the other side to make it look like the answers. So I can automatically take off the ones that don't have a plus 3 at the back, because that's how my answer looks. And now the only difference between A and C is the slope part of it. And our rule for inverse ones is basically the derivative of the inverse is 1 over the derivative of the original at the corresponding value. Well, all of these ones are positive. We can see the original at this place has 5 as the derivative. So my answer is going to be C, because I just do 1 over that value. I don't have to add a negative sign or anything. That's for perpendicular. All right, so A is out because I don't need that negative, which leaves C as the only option.